This is a basic diagram that will help in making all of the explanations and discussions of the Hubble constant a lot easier to understand. Here's the Earth. Here's the galaxy at time equals 0 when the light was emitted from the galaxy. At that point in time, the galaxy was at a distance d1 from the Earth, and the galaxy had a recessional velocity of v1, and the expansion of space at that point in time was the Hubble constant h1. Now, after the light was emitted, space continued to expand, and that means that the distance the light actually traveled ended up being longer than d1. So this is the longer arrow illustrating the distance that the light traveled. And the distance that light traveled is noted as dl. And that is the distance that cosmologists calculate when they calculate the distance by various methods based on the light that's observed on Earth. The final arrow is at the time, as of the time the light is observed now. So it's the distance now, and that's the distance as if all of the units of space had expanded over time to some longer amount, and that's where the galaxy would be now if there had been no other forces at play. And for reasons that will be discussed later on in this series, the Hubble constant that is associated with that is a blended value. So I denote that as HB for the blended Hubble value. This is another way of understanding the same diagram. At time equals 0, the galaxy was so many megaparsecs away from Earth, d1. While light was in transit, as the light crossed the first megaparsec, it hadn't expanded very much. So its distance was about the same, almost exactly the same, as the original distance. By the time the light gets to the Earth, the last megaparsec of space has had a lot of time to expand. So you can see that as light is coming towards the Earth, each unit of space is getting longer and longer compared to the distance it started with, which might make it easier to see why the distance the light traveled is longer than the distance that the galaxy was when the light was emitted. The final length, dn, is simply all of those units of space from the beginning expanded fully according to the expansion over time of space. And one more point can be made looking at the basic diagram, which is that if one took this distance dl from the Earth and was to calculate the recessional velocity of an object at that distance, that would be the recessional velocity of a phantom object, because that's not where the galaxy was at the time the light was emitted. So we could denote that as Vp, the velocity of the phantom object, and it's going to turn out that this velocity is actually useful in some of the non-compounding calculations of the cosmological redshift that we're going to see later and that physicists and cosmologists use at the present time.